Hi, I'd like to welcome you to the Concrete Maths seminar at the University of New South Wales. Today, the speaker is Professor Norman Wildberger, and he's going to talk about how chromogeometry transcends Klein's Erlangen program for planar geometries.
Thank you, Michael. Okay, so I want to give you a brief introduction to sort of a new development in Euclidean geometry that's been around for the last 10 years or so, called chromogeometry. It's very exciting because it opens up our understanding, it sort of widens our understanding of what geometry is. So back in the 19th century, Felix Klein, notable German geometer, introduced this idea that became known as the Erlangen program, where he said that what geometry really is a group acting on a space, actually acting transitively on a space. So the group theory or the symmetry behind geometry was sort of elevated to a formal status. And that's been a kind of a guiding light in geometry. It kind of allows us to unify projective, affine, metrical geometry, as well as hyperbolic and other geometries. So it's been a very important principle, but sometimes important principles are not just positive, but they also may stand in the way of moving beyond them. And I think we've come to the stage now where it's time to consider going beyond Klein's Erlangen program and thinking about geometry more generally. And today's little lecture is something in that direction to sort of open up some doors for us to be able to think about geometry more generally. So we're going to start with a picture here. This is a picture of a triangle A1, A2, A3. And there's a few lines here. Prominent here is the blue line. This is the famous Euler line of the triangle, which contains the orthocenter up here. That's the meet of the altitudes of the triangles, And then here's the circumcenter, which is the meet of the perpendicular bisectors, also the center of the circle that passes through the 3 points. And there's the centroid, which is, of course, the point of balance of the circle, or the intersection of the medians. Also, there's another point here, the 9-point center, which is also prominent on this Euler line. And Euler notably discovered that these 3 points were collinear, and that furthermore there was a ratio, there was an affine ratio of 1 to 2 between the circumcenter and the centroid, and the centroid and the orthocenter. And in fact, the 9-point center is exactly halfway between these. The 9-point center, by the way, is the center of the circle, which passes through the 3 midpoints of the triangle. Okay, so that's a very classical thing. In some sense, that's really the start of modern triangle geometry, this realization that these points are collinear. And what we see here is 2 other versions of that, sort of a red kind of Euler line and a green kind of Euler line. And so it'll turn out that these are Euler lines when we look at the same triangle from relativistic points of view. So there's some relativistic geometries around, and it turns out that Euler's basic relations still hold for these relativistic geometries. So we still end up having, for example, a red orthocenter, a green orthocenter, a red circumcenter, and so on. And the relations that are exhibited with the classical story hold also in these relativistic versions. But what's even more notable, I suppose, is that there's some interaction between these 3 geometries. This is sort of the second part of chromogeometry. That not only do we can expect Euclidean phenomena to extend to the relativistic stories, but in many cases, these 3 stories will then end up interacting in a very interesting way. So, for example, here you can see that this red circumcenter is actually on the line between the blue and the green orthocenters. In fact, it's exactly the midpoint, as it turns out. And there are quite a lot of other interesting relations in that direction that contain this diagram. We'll come back to this diagram later, but I first want to sort of introduce the basic framework. So the basic framework is that of rational trigonometry, where we try to look at geometry in a very algebraic point of view, so that it will work over a general field. And that's going to be quite interesting, because then we can think about geometries over finite fields. And in our next video, our next lecture, Michael Reynolds will talk about his interesting program that allows us to really explore metrical geometries in a finite field setting. So this is the sort of theoretical underpinnings of that. So the idea is that we start with a vector space over some field, and we introduce a dot product or symmetric bilinear form. So let's say we're just in the 2 dimensions. Here is some examples of dot products. This is a plus sign, that would be the familiar Euclidean dot product. With a minus sign, that would be a relativistic dot product. So given such a symmetric bilinear form, we can define the quadrants of a vector to be just v dot v. That's the fundamental concept. And we don't take the square root, because taking the square roots is computationally actually sort of impossible, really. We just stick with this purely algebraic quantity. That's the quadrants of the vector. And if we have 2 points, a1 and a2, then the quadrants between them, some symbol here is like this kind of situation with a little rectangle. That's going to be just the quadrants of the vector between them. So in the Euclidean case, it has this familiar form. Now, then we're in a position to talk about perpendicularity, because the dot product gives us perpendicularity. And then we have these 2 fundamental theorems that hold in very great generality. First is Pythagoras' theorem, that if you have 3 points, a1, a2, a3, then say a1, a3, and a2, a3, these 2 vectors are perpendicular in the sense that their dot product is 0, precisely when this quadrant's q1 plus this quadrant's q2 equals this quadrant's q3. It's an algebraic version of the most fundamental and important theorem in mathematics. It's Pythagoras' theorem. Now, much less well known is a sister theorem called the triple quad formula, but Gennadi's told us about this in some of his lectures. So the triple quad formula is that when you have these 3 points, so that the 2 vectors a1, a3, and a2, a3 are parallel, then that situation is characterized by this particular relation between the 3 quadrants between the 3 points. q1 plus q2 plus q3 squared equals 2 times q1 squared plus q2 squared plus q3 squared. So this is a little bit algebraically more sophisticated than this one, but in some sense they're kind of sisters theorems. And in my opinion, these are the 2 most important theorems in mathematics. Okay, so now what about angles? How do we replace angles in this rational setting? Well, we introduce something called the spread. And that's also directly defined in terms of the dot product. So if we have 2 vectors v and w, then the spread between v and w is by definition this quantity here. So let's have a look at that. So it's 1 minus v dot w squared over the quadrants of v times the quadrants of w. Or purely in terms of dot products, this expression here. Now in the Euclidean plane, we have a situation that looks like this. We get 1 minus this quantity here, and then there's a beautiful relation going back to Diophantus, probably, that allows us to rewrite this in this more compact form with a little determinant in the numerator squared. Okay, so this, in the Euclidean case, this allows us to measure the separation between 2 intersecting lines in a novel way, the spread going from 0 to 1. This is actually a spread protractor that Michael Ostman created quite some years ago when I first introduced rational trigonometry. Now, this Euclidean formula here, just mentioned quickly, allows us an interpretation of the spread in a kind of a physical way. What we're really doing is we're just taking the parallelogram formed by v and w and taking its area and squaring that and sort of normalizing it by the product of the quadrants of the 2 sides. It's a very simple, direct, geometrical appreciation of what the spread looks like. Okay, and then trigonometry has to do with a triangle. In a triangle, a1, a2, a3, there are then going to be 3 quadrants, q1, q2, q3, and 3 spreads, s1, s2, s3. And the idea of trigonometry is to explain the relationships between these 6 things. And there are 3 fundamental laws, in addition to the Pythagoras and triple quad formula we've already seen. So the first is the cross law that tells us how to relate a single spread in terms of 3 quadrances. The spread law, which is the analog of the sine law, S1 over Q1 equals S2 over Q2 equals S3 over Q3. And then the triple spread formula, which is a kind of cubic extension of the triple quad formula, which gives us the relationship between the three spreads of the triangle. So these are versions of the trigonometric story that are valid more generally because they're purely algebraic, and so they work over general fields. And they work, in fact, over general quadratic forms or bilinear forms. So it's a more general and encompassing framework for geometry. Let's note that as a special case of the spread law, this one here, if we consider a right triangle with S3 equals 1, that's the same thing as being a right triangle, the spread is 1, then we see that S1 is equal to Q1 over Q3. Okay? So that gives us another geometrical interpretation of what a spread is. You make a little right triangle, and then its opposite quadrants divided by, say, hypotenuse quadrants. It's like the sine squared of an angle, but we don't need angles, which are ultimately transcendental notions. We don't need the sine function, it's also a transcendental function. Okay, I'll just give you one proof. So here's the proof of the cross law. It's actually the most fundamental law. So suppose we have our triangle like this, and we're interested in Q3, okay, which is the quadrants between A1 and A2. And we can express this vector as the difference between the vector A3, A2, and the vector A3, A1. So we can take the dot product of that vector with itself. Now what happens when you do that dot product by distributive law? The A3, A2 dot with itself, that's Q1. This one here dotted with itself is Q2. And then the cross terms give us minus 2 times the dot product of A3, A2 with A3, A1. And now we recall that the definition of the spread is something similar. It's 1 minus this dot product squared over Q1, Q2. And so we can replace this dot product here by what it's equal to in this here. So I rewrite it as Q1 plus Q2 minus Q3 over 2. So we substitute this in, and we get that expression there. And that, once we clear denominators, is the cross law. So a very simple proof of a law which actually encompasses the usual cosine law, but it's more general and more powerful. Okay, so now let's just try to make a shift now towards the relativistic geometry. So I've talked a little bit about examples in the blue stories, and now let's look at moving towards the relativistic geometries, where the same framework applies. Let's start with Pythagoras' theorem in the familiar Euclidean setting. So here's a right triangle. So blue perpendicularity. So Euclidean geometry, I like to think of that as the blue geometry. So whenever I say blue, it refers to the Euclidean story. So here we have some blue perpendicularity here. So this is the blue perpendicular triangle. And here are the three quadrances represented physically. The quadrances physically represent areas of squares that are built on the sides. This is just exactly the way Euclid thought about Pythagoras' theorem. So to Euclid, Pythagoras' theorem was not a property of three lengths. It was not one length squared plus another length squared equals a third length squared. That common formulation is actually the wrong way of thinking about Pythagoras. So it's much, much better to think not in terms of squares of lengths, but rather in terms of quadrances directly, and these are areas of squares built on the sides. This one here is 20 area, this one is 5, this one is 25, which you can actually see just by cutting and pasting. And there's the Pythagorean relation. Okay, so now let's go to the red geometry. The red geometry is governed by this relativistic dot product. x1, y1 dot x2, y2 equals x1, x2 minus y1, y2. Just the same as the Euclidean one, except there's a minus sign here. And that has a lot of consequences. In particular, perpendicularity looks different. So this is actually our right triangle in the red geometry. Okay? This side here and this side here are actually perpendicular. If you wrote out this vector and you wrote out this vector and you took your dot product, you'd see we get 0. And how can we sort of see that geometrically? Well, from our point of view, living in our sort of Euclidean world, you can think about it this way, that if you look at a line of slope 1, passing through this vertex line of slope 1, that these two sides are symmetrically placed with respect to that slope 1 or slope minus 1 line. Okay, so an ordinary Euclidean reflection of this line in this line of slope 1 will give you this one. So that's a way of thinking about what perpendicularity means in the red setting. And then here then are the three red squares built on the sides, and their corresponding areas in a signed area setting. You need to, it's not absolute values, these are signed areas. So they turn out to be 12, minus 15, and minus 27. And if you take the 12 and you add the minus 27, you do indeed get minus 15, and that's the manifestation of the Pythagorean theorem in this relativistic red geometry. Now in the green geometry, the dot product is this one, x1, y1 dot x2, y2 equals x1, y2 plus x2, y1. And this is an example of green perpendicularity. So green perpendicularity to us just means that the two sides are symmetric with respect to either a horizontal or vertical line. So you just reflect in this horizontal line here, then this line is reflected in this line. That's what perpendicularity in the green setting looks like to us. So this is a green perpendicular triangle, green Pythagorean triangle, and here are the corresponding areas. The areas are the same as the areas everywhere. The areas are just affine quantities. They're the number of little squares that fill this thing up. And so this, but with a corresponding sign. And this is 24, and this is minus 6, and this is 18. And sure enough, Pythagoras' theorem holds. This diagram's not quite right. This point should actually be over here. This should be a proper parallel here. Okay, so we have these three geometries. So exactly the three that I've just described. The standard Euclidean one, and then this red one, which is a relativistic one, and the green one. Both the red and the green are actually relativistic geometries. So, and they're somehow sort of very closely connected, but it's very important from this point of view to keep them separate, think of them as sort of separate entities. And so here is a manifestation of how these three geometries interact in a very elementary way. So here's a line, L, and here's a point A. And we're looking at perpendiculars, or altitudes, from A to the line L. The blue one here is the familiar blue altitude. And here is also the red altitude to the line, and the green altitude to the line. Okay, so we have red perpendicularity there, and green perpendicularity there. And so we have these three altitudes emanating from A. And what you notice, perhaps, is that there's some interaction between these things. What do we see? Well, the blue altitude and the green altitude, for example, they happen to be red perpendicular. The blue and the red altitudes are green perpendicular, and the green and the red altitudes are blue perpendicular. So it's not just that we have the same kind of phenomena as in the Euclidean case happening in the red and the green stories. That's true. But moreover, these three geometries are interacting. We want to look at them all at the same time. So that means we don't want to restrict ourselves to just one group, as Klein would have wanted us to do. We need to think of a bigger picture where there are actually, in this case, these three groups, these three different geometries, which are interacting to form a bigger geometrical kind of situation. Okay, so now let's return to the Euler line story. Let me just explain a little bit more what's happening there. So here's the classical story. Again, the same triangle that we started with, A1, A2, A3. Here is the circle in blue. And here's that 9-point circle that I mentioned, the circle passing through the three midpoints. It also passes through some other points. It also passes through the feet of the altitudes, the sides. And here's the 9-point center, the orthocenter, the centroid, and the circumcenter. Okay, so that's very familiar. And now, it turns out that the same story is occurring in the red geometry. So there's a bunch of theorems here in this picture. The theorem is that the three altitudes of the triangle meet at a point, and that's the orthocenter there. So let me see if I can sort of illustrate this. So let's say we're interested in the altitude from A3 to A1, A2. In the red geometry, what does an altitude look like? It looks like what you get when you reflect this line in a line of slope 1. So if you imagine a line of slope 1 like this, and reflecting that, then you'd get a line that looks sort of like this. So this would be the line, which is the altitude from A3 to the side A1, A2, and it does pass through this point. Similarly, the other two altitudes also pass through. So there's the orthocenter. There's the circumcenter, which is now the center of a red circle. Red circle is a hyperbola with equations something like x squared minus y squared equals k. Okay? And that's the circle there, you can see it. That's the circle, the red circle, which passes through the 3 points. And there's its center. The 9-point center right there, that's the center of the circle, which passes through the 3 midpoints. And you can see that 9-point circle right there. That's its midpoint. And lo and behold, Euler's relation holds exactly. So that these 4 points are all on a line, we can call the red Euler line, and moreover there's a ratio of 1 to 2 between the centroid and the circumcenter and orthocenter, and the 9-point center is exactly the midpoint of the orthocenter and the circumcenter. So everything's happening in the red geometry just as it does in the blue geometry, at least in this story. And what about the green story? Well, it's exactly also the same. And here's the corresponding picture for it. There's a green Euler line, a green orthocenter, a green circumcenter, a green 9-point center, and here are the corresponding green circles. So there's this, and this is the green circumcircle. That's an equation, something like x times y equals k. That's your typical green circle. Okay, so that's great. The Euler line story extends to the red and green geometries. But now we can put them all together, and that's sort of the really interesting part of chromogeometry, is that when we put things together, we often find additional remarkable relations. So as I've already pointed out, here's this what I call the omega triangle, which is the actual triangle formed by the 3 orthocenters. The blue, green, and the red orthocenters. That's a sort of secondary triangle associated to the original triangle A1, A2, and A3. And the 3 Euler lines that we've been talking about are just then the medians of this omega triangle. Because the circumcenters are the midpoints of the sides of these things. This red circumcenter is the midpoint of these two. This circumcenter is the midpoint of these two. And this green circumcenter is the midpoint of these two. And so from that point of view, the relationship, the 1 to 2 relationship that Euler discovered is simply a manifestation of the way that the medians of a triangle bisect each other, or intersect each other in the ratio, familiar ratio of 1 to 2 at the centroid. And then there's also corresponding facts like the line, sort of things are repeated here. There's a similarity. The triangle of 9-point centers is similar to the triangle of the original one and so on. But actually, the story becomes even more interesting when we throw in the actual circles that we started with. So there's lots of things to look at here. But let's say you look at the blue circumcircle, it's the ordinary Euclidean circle that passes through the points of the triangle. Then we see that the red circumcenter is actually on that. And in fact, the green one is... Oh, no, that's actually, that's a coincidence, I'm sorry. Forget about that one. Let me say it this way. That blue circle has on it the green and red orthocenters. The circumcenters, like the green and the red, are actually on the blue 9-point circle. So here's the blue 9-point circle. and it contains the red and the green circumcenters. And then that all is repeated with respect to all the other colors, so that the green and the red circumcircles have the same kind of properties. It's a nice threefold symmetry in the entire story. Okay, so I want to now say a little bit about some other conics and how chromogeometry gives us new insights into ellipses, hyperbolas, and parabolas. So here is a familiar ellipse, the Euclidean ellipse. It happens to be centered at the origin, fine. And I've shown you the foci, so there's a focus F1 and F2. And here are the directrices, D1 and D2. I remind you that the Papian definition, characterization of the ellipse is that a point on it can be characterized in terms of the, classically, the distance to the focus and the distance to the directrix, that ratio is constant. Now, it's not hard to make that in a rational formulation by just squaring it. So what we would rather say is that the quadrants of a point on the ellipse to the focus divided by the quadrants to the directrix is a constant, which has a certain value less than 1. But here, for something a little bit novel, I show you a new characterization, or somewhat novel characterization of the ellipse, in terms of 2 second, maybe unfamiliar lines, which I call the diagonals. So here's a line L1 and L2, and I'm characterizing the ellipse by the fact that the quadrants from point A to L1 plus the quadrants to L2 is a constant k. That's another way of characterizing an ellipse in terms of 2 diagonal lines. And those diagonal lines are unique and are, I think, quite interesting. Also, the quadrilateral that they form by intersecting there is parallel to the directrices. And now, whenever we discover a phenomenon in the Euclidean case, it's natural to ask how does it look in the relativistic cases. And here we see that same ellipse, and in fact, here are its red diagonals. So it's characterized also by the same kind of equation, that the sum of the quadrants is to these 2 fixed lines is constant. That's another characterization of an ellipse. And, not surprisingly, there's also a green version of that. And now I want to have a look at this focus directrix story for the same ellipse, but now incorporating also the red and the green foci and directrices, and we'll see that there's an interesting surprise. Okay, so just focusing on the ellipse first, and the blue foci, there's 2 of them, and the blue directrices, there's 2 of them there. Okay, so these are the familiar foci, directrices of this ellipse. Now, if I just gave you that ellipse, drew it on a paper, and asked you where are the foci, it's not entirely trivial to find the foci and the directrices. So let's just keep that in mind. Now, I'm also showing you red directrices and foci. So let's say this point here, that's a red focus, and its corresponding directrix is this. So what do I mean by that? I mean that the same ellipse, when viewed in the red geometry, so with the red quadratic form, can be characterized by exactly that same kind of relation, that the quadrants to the focus divided by the quadrants to the directrix is constant. Okay. But now, we don't get just 2 foci, we get in fact 4 foci. There are 4 foci and corresponding directrices that have that property. So we could characterize the same ellipse in terms of this focus and this directrix, but also in terms of this focus and this directrix, or this focus and this directrix, or this focus and this directrix. So in the red geometry, an ellipse actually has 4 foci and 4 directrices. And exactly the same happens in the green story here, the green foci, and here are the green directrices. Now there's something in addition which is surprising here. If you stare at this for a little while, you will perhaps discover that there's quite an interesting relation between these foci, these four foci, and the ellipse. And it's clear if I look at the green situation. So have a look at these green foci. There's one there, one there, one there, and one there. What relation do they have with regard to the ellipse? Well, as I'm suggesting by the motion of the mouse here, they're exactly the corners of a box that circumscribe the ellipse. And this rectangle is exactly one with horizontal and vertical sides. So in other words, because we have our fixed axes, we know what horizontal and vertical is. If we want to find these green foci, one way of doing it would just be to put the ellipse in a box in the simplest possible way, a box whose sides are parallel to the axes. So you find a tangent line which is vertical here, a tangent line which is vertical here, a tangent line which is horizontal here, and the corners of that are automatically the foci. And moreover, the places or the contact points where those sides meet the ellipse, like this point here, and this point here, and this point here, and this point here, are exactly determining the directrices. That point there's the contact point of the tangent, there's the contact point of the tangent, and that's a green directrix. For the red story, it's exactly parallel, except that now sort of the null lines in this red geometry are at slope of 1. So it's the same kind of thing, but now we have to put the ellipse in a box whose sides are of slope 1 and -1. That was 45 degrees in the usual fashion. So if you just put the ellipse in such a tilted red box, then automatically you get the foci as corners, and you get the directrices as the intersection of tangent points of the sides. So somewhat remarkably, we see that there's actually something quite different happening in the red and green geometries, that there's 4 foci and 4 directrices, and these are much closer aligned with the geometry of the ellipse than in the blue setting. If we had to find the foci of a red ellipse, it would be a much easier job than it is in Euclidean geometry. We just create this box, and that's the end of the story. Now, if you stared at this a little bit further, you might also start to suspect that there's something else going on a little bit. Just have a look at this region here, okay? Where we're looking at these 3 directrices, this blue one here, and this green one here, and this red one here. So that little triangle. Okay? It looks like the 3 foci are almost at the vertices of that triangle, almost, but not quite. They're kind of close. So it turns out that when we get to the parabola, something even more remarkable happens, and that seeming closeness that we saw in the ellipse case becomes exact. And we get an entire new phenomena for the parabola. So let me show you here. So here's a parabola. Okay? And in the Euclidean situation, you all know that such a parabola has a focus, which is this blue point, and a directrix, which is this blue line, and that the points on the parabola are characterized by having equal distance, or better yet, equal quadrants, from the point to the focus, and from the point to the line, the directrix. Now, this same parabola can be viewed also as a parabola in the red geometry. And then it turns out that the focus is this point here, and the red directrix is this line here. This is the red directrix, this is the red focus. And similarly, the green focus is over here, and the green directrix is over here. And remarkably, we see that these three foci, the blue one, the red one, and the green one, also determine the directrices. The blue and the red foci determine the green directrix. Similarly, the blue and the green foci determine the red directrix, and the green and the red foci determine the blue directrix. So this little triangle that we see here, if you stare at that, the triangle of foci itself has nice properties because the red side and the green side are actually blue perpendicular. The red side and the blue side are green perpendicular, and the blue side and the green side are red perpendicular. So this is a triply perpendicular triangle. It has a right angle in the blue setting and in the green setting, and also in the red setting, different corners. Now, in the industrial world, important aspect of the parabola is that it has a reflection property. So if a particle is coming in here parallel to the axis, okay, what is the axis of a parabola? The axis of a parabola in the green setting, or in the blue setting, let's say, is a line through the focus, which is also touching the line at the point infinity. So a parabola can be characterized by being a conic which is tangent to the line at infinity. That's a real nice projected way of thinking about it. So it's tangent to the line at infinity, and the direction of that tangency is exactly the direction of the axis. So the blue axis is going through the blue focus and going up in that direction. But from the red point of view, there's also it also has an axis, but the axis is in the same direction, but it goes through the red focus. So the red axis will look like this. That would be a line of symmetry in the red geometry of this parabola. And the green axis, through the green focus, also in the same direction, will be a line of symmetry in the green geometry. And now the reflective property is that if you have a particle coming in this axis direction, the axis direction is the same for all three geometries. It's determined by the unique point at infinity on the cone. If that's coming in like that, then here's the tangent line, it will reflect. What does it mean to reflect? Well, it means that that the angles are equal in the classical setting, but more generally, in this more general context, it means that the spreads are equal. Okay? That the spread made between the tangent and the incoming line is going to be the same as the spread made by the tangent and the outgoing line. And in the blue story, the Euclidean story, we all know that the reflecting property is that the line coming in parallel to the axis will reflect off the parabola and head towards the focus. Or in an automobile headlight, if you have a light bulb here, then all the light that's emanating will bounce off the parabola and it will all end up being parallel, so you'll have a focused beam in the direction of the point at infinity. And what I'm saying here is that exactly the same phenomena happens with the green and the red geometries. So if we take this line coming in here and we reflect it off that same tangent, but now reflect it in a red way, it passes through the red focus. And if we reflect it in a green way, it goes through the green focus. And there are quite a few other nice properties of the chromatic parabola, which is, I think, a nice indicator of the power of chromatic geometry. Okay, so in terms of some references, well, this is my book on rational trigonometry, which starts the story. And then there's the various articles on chromogeometry and relativistic conics. There's one, Mathematical Intelligence, about 10 years ago. That's the cover story for the spring 2010 version. There's a picture of the chromatic parabola. And then there's a couple of papers with Nguyen Lê and myself on further aspects of triangle geometry involving the in-center story, which is another very interesting story that I'll tell you about later at some other point. And then there's my YouTube series, the Wild Trig series, talks a little bit about this, the Universal Hyperbolic Geometry series talks a little bit about this, and also in the Math Foundation series, which is now getting very extensive. There's also some stuff in there. So to summarize, we now see that geometry, planar geometry, we're really talking only about the plane, has this intrinsic threefold symmetry that brings together Euclidean geometry and two relativistic geometries. So purely from a geometrical point of view, relativistic geometries could have been discovered hundreds of years ago, just in the context of what's happening with planar geometry, extending Euclid. And so there's two aspects of this chroma geometry. Sort of the elementary aspect is that if you have a theorem in Euclidean geometry, there ought to be some kind of analog of it in the red and the green geometries. So there's thousands of theorems in Euclidean geometry, so there's a lot of work to go around identifying and correcting and finding the correct versions of the relativistic analogs. And then there's the second, more deeper aspect of chroma geometry, that once you have these three pictures happening in the same plane, that there very likely is interaction between them, and that there's some kind of rich symmetry, threefold symmetry in this situation that's, I think, completely surprising and completely unpredicted by classical mathematics. So I think it really is time for us to broaden our horizons and go past Klein's program. Thank you.
Thank Norman for the talk, and ask now if there are any questions. Actually, I have a couple.
Yes, Mike.
In the case of the blue geometry, where are the missing foci and directrices?
Yes, that's a good point. So they are there, but one has to sort of complexify things. So if one complexifies things, then one can find those points. And in fact, then the same kinds of relations that I mentioned for the red and the green are visible then in the blue story.
Okay. So if you had a bilinear form that you were transforming, you would take, this is going to be true with a general bilinear form, much of this, is it not?
Yes, yes.
So imagine you've got a matrix and you're transforming it slowly from, say, the red towards the blue. Is there some point where something happens that they...
Yeah, it's a little bit perhaps like, you have a polynomial and you're looking at its zeros, and at some point it has got 4 zeros, and then at some point you change the coefficients and suddenly 2 of them disappear and they become complex.
Right.
And so the thing is sort of moved.
Okay.
So there'll be a sort of a tangent point that will characterize that exact point. You'll have a multiplicity or a doubling point before you transition from one situation to another.
Okay. And second, unrelated question, the group theory behind some of this. Can you just mention very quickly what's lying there? Yeah, so behind the three geometries are these three quadratic forms, and probably one should think about them in terms of 2x2 matrices, so symmetric matrices. And so each of those 2x2 matrices has a group of transformations, linear transformations that preserve them. And so those three groups are going to also interact in some interesting way, which hasn't really been explored. But if the three geometries are interacting, then it's a good guess that the three groups are also interacting. Right. So there'll be an algebraic aspect of this, but I don't know too much to say in that direction at this point. But I think that's an interesting question and probably an important thing to think about. Any other questions? Yes?
Got a couple. So I sort of saw with the blue, red, and green geometry that there's sort of like a transformational approach to it. Would you care to sort of...
What do you mean by a transformational approach?
You sort of look at red geometry, like the red perpendicularity just by reflection on sort of one line, as well as green geometry also at that. So would one be able to sort of look at chroma geometry from a purely transformational approach?
You might be able to. I do think it's probably likely that there's a symmetry there that, I sort of gave it to you from the point of view of the blue, being versed in blue geometry and visually being able to see blue geometries intuitively. But probably the same kind of relations hold in the red and the green, from the red and the green point of view. So if we were So yeah, I think that might be related to Michael's question about looking at it from the group theoretical point of view and what are the isometries, what are the symmetries of the geometry. So that is Klein's point of view, that the symmetries of something is really important. But I guess what we're saying here is that there's three different groups of symmetries and they're interacting in some kind of novel way.
Yeah. So I guess to comment on Michael's point as well, I think like when you sort of consider the 2x2 matrices that represent the three various homogeometries measured by default, I'm not mistaken, they do form a basis for the 2x2 symmetric matrix.
Yeah, there's one more. Those three matrices. There's also an anti-skew symmetric matrix that you have to throw in. And that sort of corresponds to sort of parallelism. So.
Yep. And my last question is, what are your thoughts on the possibility of the maybe possible existence of chromogeometry in three-dimensional space?
Yeah, that's a really good question. The question is, what about chromogeometry in 3 dimensions? That's a really good question. I have no evidence at all that there is such a thing. So I would not go so far as to speculate that there is such a thing or conjecture. I don't have any evidence at all, but I would be very interested to find anything like in that direction. But I don't know of anything that suggests that. So it might be that this is entirely a planar phenomena, or it might be that we just don't understand what's going on. That things become a lot richer in higher dimensions. I don't know. It's definitely an obviously good question.
Any other questions? Yes.
If you have an ellipse, how do you find the two diagonals?
How do you find its two diagonals? That's a good question. I forget offhand.
But there is like
I think there's. I'm not sure if there's actually a nice construction for them that I know of. I still have an algebraic, version of them. But physical construction, I'm not sure. Certainly, I can't remember if there is. That is also a good question. The diagonals of the ellipse is something that should be thought about a little bit more. Yeah.
And that's a new thing, isn't it?
I think so. I think so.
Yeah.
It's a little bit surprising if it is, but it's hard to say. In the 19th century, people knew so much that we sort of lost touch with a little bit. So maybe it's certainly not well known.
Mm-hmm. Other questions? In that case, I'd like to thank Norman again, and very interesting talk as usual. Thank you.
Thank you.